back to Sophia's chemistry class, where today we're going to be talking about the structure and properties of matter. Our main topic of discussion today is going to be subatomic particles and their behavior. But the first iteration of the entire particle theory comes from ancient Greece, where Democritus thought that the atom, then called the atomos, was the smallest particle in existence and belonged to one of four elements: earth, wind, fire, or air, kind of like Avatar. And that notion was generally respected until the Middle Ages, but especially in 1803, when Dalton conceived of the billiard bar model, and that explained the law of definite proportions, the law of multiple proportions, and the conservation of mass law. But in 1897, Thomson discovered that matter was able to conduct electricity, and from that he was able to conceive of the plum pudding model, which was that the atom had positive and negative charges all throughout in any random order. But that was later disproved again by Rutherford, who shot alpha particles through the atom, and he found that the direction that the particles left the atom in were completely obscured. And from that he was able to determine that the arrangement of protons and electrons within the atom. He found that there was a very dense, positively charged nucleus that was surrounded by negatively charged electrons. And from that, he created the planetary model, which is mostly what we teach in younger science grades. Now, the planetary model says that the positively charged nucleus is surrounded by electrons. But the problem with this model is that the electrons would become very attracted to the protons in the nucleus, and they would slowly lose energy as they get closer, emitting light, and the atom would eventually collapse upon itself. See, Bohr knew that there was a problem with this model, and that's why he came up with the hydrogen spectrum to explain the problems within the planetary model. However, his explanation is not fully realized because it's only applicable to hydrogen, and not even he understood the complex reasons why it worked for hydrogen. Essentially, he said that electrons can move in orbits around the nucleus, but they cannot change energy levels unless they gain or lose energy. And a few years after the planetary model was founded by Rutherford, Chadwick and Rutherford discovered the presence of neutrons within the nucleus by determining that the total mass of the atom was not nearly enough to encapsulate the combined mass of the electrons and the protons within the. When it comes to actually mapping out the electron, that's not the right word. When it comes to actually mapping out the atom, it's basically impossible. And that's because, according to Heisenberg's principle of uncertainty, it is essentially impossible to know the exact location and behavior of an electron or any subatomic particle for that matter. What we do know, however, and what we can do, is we know that electrons exist in orbits, that they revolve around the nucleus in rings, or more realistically, waves. But the first ring, or the closest area that the closest electrons are, is called the first orbit, and it's given the number n equals 1. And the second, where electrons may exist, is called n equals 2. And this Bohr-Rutherford diagram is what we learn and what we use within the first 3 years of high school. However, what we did not learn in younger grades was that within the orbits there are suborbits known as orbitals, areas within the orbit which electrons are most likely to be in. And there are 2 electrons per orbital, meaning that if you recall that in the Bohr-Rutherford diagram, when in the first level only 2 electrons were capable of fitting in, that's because there's only one orbital within the first quantum number, within the first energy level of 1. The amount of orbitals present within an element depends entirely on the energy level of the element, because the first energy level of 1 is only has one s orbital, and the s orbital is only able to hold 2 electrons. So this means that the first energy level only can hold 2 electrons. Now the second energy level has both one s orbital and 3 p orbitals. This means that it can hold 1, 2, and then the 2 p orbitals, 1, 2, 3, 1, 2, 3, 4, 5, 6. So it can hold 8 electrons in total. And if you remember, this is exactly the same as in the Bohr-Rutherford diagram, where the first orbital could carry 2 electrons, and the second could carry 8, and then 10, and then 18, and so on and so forth. As the energy level increases, the amount of total orbitals within the orbit and the amount of electrons it can therefore hold increases as well. This is why larger elements, atoms, can hold so many more electrons than smaller ones like hydrogen. We make energy level diagrams like the one I just made to find out how many bonding capacities a specific atom has before it's ionized. So let's take fluorine for example, knowing that fluorine has 9 electrons. So of course we start with 1s because that is the first orbital in any element. And it's going to be filled up by 1, 2 electrons. If you notice I'm going 1 up and 1 down, this is to symbolize that one electron is spinning up in an orbital and the other is spinning down because they're avoiding each other in accordance with the Pauli exclusion principle. And the next orbit and orbital of 2s is going to do the same. Another 3, 4. Again, going in opposite directions. You'll notice that I'm fully filling the 1s orbital before I'm even touching the next energy level or the next orbital. And this is because this needs to be fully satisfied according to the Aufbau principle, where the lowest energy orbital is satisfied first because the attraction that the electrons feel from the nucleus is stronger. Next would be the 2p orbital, and there's 5 electrons that still need a place, and there's 6 places there's 6 places for an electron to be in within the p orbital, but let's fill it up. 1, 2, 3. Notice I'm filling up each one first because they all need to be satisfied or else it would collapse. 4, 5. And there's still one missing area for an electron. This means that fluorine has one area where an electron from another atom, could come in and ionize fluorine to make it stable. With an energy level diagram, we're able to identify specific electrons based on a series of numbers given to us. And those numbers given to us are called N, L, ML, and MS, where N is our energy level, which is essentially the distance from the nucleus to the specific level where the electron we're looking for is. So let's say, for example, the electron we're looking for is right here. Well, we don't know that yet, but they give us the number 2 because the difference between the nucleus and the electron we're looking for is a value of 2. So our N value is equal to 2. And what does this mean? Well, just that. The electron is 2 away from the nucleus. Next, our L value. They told us that our L value is equal to 1. What does this mean? Well, L values are given value because they tell us exactly where our orbital is, or what our orbital is. If the L value they gave us was 0, then we would know that we would be in the s orbital. If the L value they gave us was 1, then we'd be in the p range, meaning there'd be 3 possible spots where the electron could be found. If our L was 2, then we'd be in the d range, meaning there'd be 5 possible spots. And if our L was 3, then that means we'd be in the f range, where there's 7 possible areas where our electron could be found. Luckily, we're in the p range, so we know there's only 3 places we need to be looking for. Next, they tell us that our ML value is 0. What does this mean? This means that out of the 3 areas where our electron could be found, it's found in between -1 and 1. So essentially, imagine our L value was 2. That would put us in the D range, meaning our M1 could be anywhere from -2 to 2. And if our L was 3, then our ML could be anywhere between -3 and 3. So, in between -1 and 1, there's 3 different areas. And if they gave us -3, we would be in the first range. 0 means we're in the second range. And third means we're in 1 means we're in the third orbital. They gave us 0, so we know that we're in this orbital. But we still don't know which electron we are until we find out our spin. And they tell us that our spin is -1/2. Recall how 2 electrons can fit in every single orbital. I'll write it up here. One spins up. This is the +1/2, and one spins down. That is the -1/2. Since they tell us that our electron is a -1/2, and it's within the middle orbital, we know that everything here must be satisfied first before anything could go down, in accordance to the Hund's rule, which basically says that these electrons are trying to run away from each other. They do not want to be near each other unless they absolutely have to. So there will never be a negative spin unless every single orbital is already satisfied. So since there is a negative, and we know that it's 0, we know that it must be over here, meaning it is the 5th electron within the 2p orbital. The last thing we're going to be covering today is bonding on an atomic level. And essentially, as you might recall, there are 3 types of bonding. There's metallic, ionic, and covalent. And the way metallic works is essentially there are delocalized nuclei floating around and electrons just hanging out between them, sharing between all of them. And this is because metals all have very low electronegativities, meaning none of them are very eager to grab onto an electron and hold it. That's the complete opposite of ionic, where essentially the cations and the anions have such drastic electronegativity differences that one is just willing to give away their electron or electrons completely, and the other one is willing to just grab it from them with like no remorse. But covalent bonds, on the other hand, are an equal partnership where they are sharing one or multiple electrons. And the way that works, sometimes, one of the ways that works is through sigma bonds. And let's use fluorine, for example, which, as you recall, has 9 electrons. So fluorine, we'll draw the energy level diagram, has 1 s orbital in the first quadrant, orbit, an s orbital in the second quadrant, and 3 p orbitals in the second quadrant as well. This leaves one area where an electron needs to be for the fluorine to be completely satiated. And say we're making hydrogen fluoride, the energy level diagram for hydrogen is simply meaning this also only needs 1 electron to be stable. So these two can just share them with each other, making both of them completely stable and creating hydrogen fluoride. However, in some cases, like in the case of carbon with 4 hydrogens, for example, because carbon has a bonding capacity of 4, how is it able to bond with so many different elements when 4 is essentially impossible for many others? Same thing with phosphorus, when it's able to bond with 5 other elements. The way it works is through a process called hybridization, where different orbitals combine with each other to form orbitals on equal levels so that there can be multiple bonds. So the carbon has 6 electrons. So we'll draw the energy level diagram for carbon. Notice how even though there is 1, 2, 3, 4 electrons missing for carbon to be fully stable, this is impossible to fill up because it's fully empty, so it's not stable, and these two only leave it with 2 to be filled up. So what it does is it merges the 2p and the 2s orbitals to form 4 orbitals, each with 1 electron in them. And these orbitals are all called sp3s because 1 of them is from an s and 3 of them are from p's. And they're all equally as accessible. So a hydrogen, because if you recall, it looks like this, could come in and fully fill it up, creating SCH4.